let's use some rotational quantities to describe some motion. We're having a bicycle mechanic mount a bicycle on a repair stand and start the rear wheel spinning from rest to a final angular velocity of 250 revolutions per minute in 5 seconds. And we want to know the average angular acceleration in radians per second squared. We'll begin by reading the problem statement, as I just did, and then trying to extract information. From rest means that our initial velocity is going to be 0, which means that our initial angular velocity is also 0. We have a final angular velocity of 250 revolutions per minute, so we can also write that down. What else? We know that we want our average angular acceleration. We can specify our initial position as theta equals 0. And now we want average angular acceleration. We have an equation for that. It's going to be the change in angular velocity over time. So we'll write down our equation and see if we can plug things in. We have all this information. It's going to be final angular velocity minus initial over time, which gives us an answer of 50 revolutions per minute per second. That might not be what we want, though. It says that we want it in radians per second squared. We have to do a unit conversion of revolutions to radians to make this work, and this minutes to seconds to make this work. This is going to be a common unit conversion that you're doing here, so get used to it. To get from revolutions to radians, it's a 2 pi ratio, and to get from minutes to seconds, it's 60 seconds. We can then cancel out the revolutions and cancel out the minutes, and we're left with an answer in radians per second squared of 5.24 radians per second squared as our average angular acceleration. Next, the wheel's spinning, she hits the brakes, and we have an angular acceleration of negative 87.3 radians per second squared. We want to know, how long does this take the wheel to stop? We'll write down what we know from the problem statement. And we know the wheel's stopping at the end, so our final angular velocity is 0. Our initial angular velocity is however fast it was spinning at the end of part A, which was 250 revolutions per minute. And now we can try and solve. We'll use the same relationship, alpha bar is equal to delta omega over delta t, and solve for the thing we want to know, how long, which is delta t. You can flip over both sides and multiply by delta omega to get delta t is equal to delta omega over alpha bar. Plugging in values, we can evaluate this, noting again that we have revolutions per minute over radians per second squared, so we need some unit conversions here to make this work. And it'll be the same unit conversion as before. 2 pi over 60 gets us from radians per second to revolutions per minute. Finally, we're left with the amount of time it takes to brake under that sharper acceleration of 0.3 seconds.